Today we will discuss some theorems related to ideals. So the statement is prove that an ideal S of a commutative ring R with unity is maximal if and only if the residue class ring R by S is a field. उसका proof देखते हैं. Since R is a commutative ring with unity, therefore R by S is also a commutative ring with unity. The zero element of the ring R by S is S, and the unity element is the coset S plus 1, where 1 is the unity element of R. Let the ideal S be maximal. Then, to prove that R by S is a field, let S plus B be any non-zero element of R by S. Then S plus B is not equal to S. Is that B does not belongs to S. To prove that S plus B is inversible, if B is the principal ideal of R generated by B, then S plus B is also an ideal of R. Since B does not belongs to S, therefore, the ideal S is properly contained in S plus B, but S is maximal ideal of R, hence S plus B is equal to R. Since 1 belongs to R, therefore we must obtain 1 on adding an element of S to an element of B. Therefore, there exists an element A belongs to S and alpha belongs to R, such that A plus alpha B is equal to 1. Note that B is equal to alpha B such that alpha belongs to R. Since 1 minus alpha B is equal to A, which belongs to S, consequently S plus 1 is equal to S plus alpha B, which is equal to S plus alpha and S plus B. Since S plus alpha is equal to S plus B inverse, thus S plus V is inversible. Now, since R by S is a field. Now, conversely, let S be an ideal of R such that R by S is a field. We have to prove S is a maximal ideal of R. Let S dash be an ideal of R properly containing S. Is that S is a superset of S dash and S is not equal to S dash. Then S will be maximal if S dash is equal to R. The element of R contained in S already belongs to S dash. Since S is a superset of S dash, therefore R will be a subset of S dash if every element alpha of R not contained in S also belongs to S dash. If alpha belongs to R is such that alpha does not belongs to S, then S plus alpha is not equal to S. Is that S plus alpha is a non-zero element of R by S. Also, S dash properly contains S. Therefore, there exists an element beta of S dash not contained in S, so that S plus beta is also a non-zero element of R by S. Now, the non-zero element of R by S from a group with respect to multiplication, because R by S is a field. Therefore, there exists a non-zero element S plus Y of R by S such that S plus Y, S plus beta is equal to S plus alpha. So S plus Y beta is equal to S plus alpha, which is equal to Y beta minus alpha belongs to S, which is equal to Y beta minus alpha belongs to S dash. Here S is a subset of S dash. Now S dash is an ideal, therefore Y belongs to R and beta. Therefore Y belongs to R, beta belongs to S dash, which is equal to Y beta belongs to S dash. Again, Y beta belongs to S dash, Y beta minus alpha belongs to S dash, which is equal to Y beta minus alpha belongs to S dash. Is that alpha belongs to S dash. Thus, R is a superset of S dash. Also, S dash is a superset of R as S dash is ideal of R. Since therefore S dash is equal to R. Hence, the theorem is proved. Now there is another theorem. Let R be an commutative ring and S is an idle of R, then the ring of residue classes R by S is an integral domain if and only if S is a prime idle. So the proof is, let R be a commutative ring and S an idle of R. Then R by S is equal to S plus A such that A belongs to R. Let S plus A comma S plus B be any two elements of R by S. Then A comma B belongs to R. We have S plus A, S plus B is equal to S plus AB, which is equal to S plus BA. Since R is a commutative ring, which is so this is S plus B, S plus A. Since R by S is a commutative ring, now let S be a prime idle of R. Then we have to prove that R by S is an integral domain. For this we have to prove that R by S is without zero divisor. The zero element of the ring R by S is the residue class S itself. Let S plus A, comma S plus B be any two elements of R by S. Then S plus A, S plus B is equal to S, the zero element of R by S, which implies that AB belongs to S. Either A or B is in S. Since S is a prime idle, either S plus A is equal to S or S plus B is equal to S. A belongs to S, which implies S plus A is equal to S. Either S plus A or S plus V. S plus B is a zero element of R by S. Therefore, R by S is without zero divisor. Since R by S is commutative ring without zero divisors, therefore R by S is an integral domain. Then we have to prove that since R by S is commutative ring without zero divisors, therefore R by S is an integral domain. Then we have to prove that S is a prime idle of R. Let A comma B belongs to R. Then we have to prove that S is a prime idle of R. Let A comma B belongs to R such that AB belongs to S. We have AB belongs to S, which implies that S plus AB is equal to S. So S plus A, S plus B is equal to S. Since R by S is integral domain, therefore it is without zero divisor. Therefore S plus A, S plus B is equal to S. Either S plus A or S plus B is zero. Either S plus A is equal to S or S plus B is equal to S. Either A belongs to S or B belongs to S. This implies that S is a prime idle. Hence the theorem is proved.